So this is a talk on generalization bounds for neural network-based decoders. Thank you to the organizers for having me here, and thank you for all of you for coming. This is joint work. Pretty much most of the work has been done by the first author, Sudarshan Adiga, who's a PhD student. Xin Xiao, she finished her PhD, now she's at Apple, and Professors Bane and Tamal, who are at University of Arizona. So here's a quick outline of the talk. It's a little bit ambitious, so I'll skip depending on how much time Oliver gives me. So I'll start by talking very quickly about where people are using machine learning in communication systems and next generation 6G and beyond. Then I'll maybe spend 5 to 10 minutes maximum on telling you what has happened for machine learning for channel coding, a very quick overview, so that you are hopefully motivated and with me by that point. And then I'm going to talk about belief propagation, neural belief propagation, and then present the main result, which is some theory for neural belief propagation decoders. Okay. All right, so as far as the trend of using machine learning in area X, Y, or Z, as you can imagine, it has also percolated in the design of communication systems. And you can imagine pretty much every single block in the pipeline of a communication system, there has been efforts in the last 5 to 6 years, how to use machine learning and more data and design more data-driven methods for solving different blocks in a communication pipeline. Starting from designing better modulation schemes, doing better channel estimation. This is one of the key components. Designing beamforming, using spectrum more efficiently, and how to allocate spectrum, how to use spatial frequency and temporal resources. Resource allocation, if you think about edge networks, you have large number of devices which have to be packed. Okay. And of course, our most favorite, especially for this group, channel coding, designing better encoding and decoders. Okay. So this talk is of course going to be focused on the specific block, which is channel coding. More specifically within this context, I'm going to focus on design of better decoders. So I'm going to assume that I have a message M. So think of message M as a sequence of k bits. I'm going to take my k bits, map them to n bits. So throw in some redundancy for error protection against errors. Then those encoded bits are passed through a noisy channel, then passed to a decoder, which tries to come up with a good estimate of the original message. All right. Now, as far as classical decoders go, think of these as man-made or man/human-made, woman-made decoders. We have a long list of classical decoders sitting here, including bit flipping decoder, Viterbi, BCJR, belief propagation, turbo codes, polar codes, successive cancellation, list decoding, and the list goes on and on. Okay, so of course, I'm not gonna explain you every single item in the list. But if you think about what's the parallel situation as far as the machine learning side goes, turns out the list is also growing pretty quickly. Okay, and more quickly than this list grew over the last, 60, 70 years, right? So there are essentially, AI-aided counterparts of the list on the left. There are counterparts sitting on the right. So you have reinforcement learning for bit flipping, and I'm just giving you a small, appetizer of what you will see if you start searching for AI-based decoders. There is something called a Viterbi net. There's a BCJR net. There is neural belief propagation, neural successive cancellation, polar codes, turbo autoencoder, and so on and so forth. Yes, question. There are papers on that too. As I said, I will only focus on the design of decoders for a fixed encoder. You can ask all sorts of questions. Can we design them jointly? If I fix a decoder, what's the best encoder for this fixed decoder? Right. So there are many interesting flavors you can ask. Okay. So as I said, this is a partial list. So I don't want to.
So Ravi.
Yes.
So these talks, I like them because they're a bit controversial. So let me be the contrarian in the room. Your comment is not completely fair, right? Because are there machine learning aided decoders that are agnostic to what you've done on the left?
Okay. So I'll come to that. Good point. So I'll come to that point in maybe 5 minutes. So they are not necessarily agnostic in which specific sense.
So, we needed to do the BCGR to do BCGR net. Right? We needed to understand turbo to do anything. So in a way, they're refining what we know.
So there are two ways to go about designing a good decoder. either you ignore what is known about a good decoding operation, what makes a good decoder. Either you ignore that knowledge and say, let's say, I'm not a domain expert. I haven't taken a course. I haven't taken a course in coding theory. So I'm going to just show noisy examples and train a decoder and learn good decoding rules. That's one way to go about it. But then you'll have to do a lot of work in terms of optimizing that network, showing a lot of noisy code words. A better way is to use domain knowledge, as you said. And I think that's, in some sense, that's what has happened to a large extent in the papers. So yes, I did you on that.
So I mean, I'm just gonna. I'm shut up. I promise. There was a great tutorial at ITW a few weeks back on something similar. Oh, that's good. And I think there were long discussions about that for hours after the tutorial. So you get the slides if you get a chance.
So unfortunately, I have 3 more slides, which are going to praise neural or machine learning decoders. So this slide is making the point that neural decoders can outperform classical counterparts. So people have designed, for a given type of encoder, let's say a convolutional and turbo code, people have designed recurrent neural network-based decoders, so which try to achieve better performance or close to optimal performance that you would get by using, let's say, a Viterbi or a BCJR. Same thing goes for, let's say, a bit flipping decoder. So people have used reinforcement learning-based bit flipping decoders, and they give better or close to comparable performance than what we know by a man-made decoder or a human-made decoder. Same thing goes for successive cancellation decoder for polar codes. Now you may see these curves, since you can sort of ask this question. Well, they look similar or maybe tiny bit better, but it really depends what you mean by tiny bit better. If you're at Qualcomm, let's say, 0.5 dB improvement is a 50,000 raise in your salary, right? So it really depends on what is better for whom. Okay. But one thing a point I should make is consistently what we have seen in many papers is that you achieve the best state-of-the-art performance with reduced complexity. I think that's, in some sense, a good achievement, I would say. Other things people have looked at is adapting or designing decoders which can deal with channel uncertainties. So I'm giving an example of BCJRNet, where the fully connected network is used to learn the factor graph, and then then they take the decoder output by doing message passing over the factor graph. And same thing for ViterbiNet, which requires to compute the log likelihood function requires CSI. So in some sense, this method sort of jointly computes an estimate of the CSI and combines it with the steps of the Viterbi algorithm. All right, I know I'm going a little bit fast because I want to come to my work. So if you don't understand everything here, no problem at all. I will explain my part very slowly. All right. As I think one of the questions you asked was joint design of encoder and decoder. So there are a couple of papers on that as well, which is turbo autoencoder, which uses a convolutional neural net architecture to mimic the interleaved behavior of turbo. And there is a recent work on Kronecker operation-based codes, which is inspired by Polar and Reed-Muller codes, which is also very interesting. So by the way, I have some references at the end. So if you are interested in exploring more, and I think ITW tutorial with both these things, it will be a good combination to pointers for literature. All right, so I think Matthew already mentioned that typical ML architectures do not necessarily completely use domain knowledge. So there are several methods to incorporate domain knowledge for designing better decoders. So first of them is borrow the architecture. Let's say if I am doing belief propagation, as I will talk about it in a minute, it has a certain type of rules and a certain architecture, certain set of steps. So you can maybe borrow the architecture from the classical algorithm and then do something data-driven to make that better. Right? That's one approach. There's another approach which people have started to look at is learning from the mistakes made by classical decoders. So if you design a classical decoder, you know that maybe it is failing on some type of error patterns. So you can extract those error patterns, and people have done work on extracting when a certain decoder fails. And then you can use those error patterns and then show them, in some sense, think of these as adversarial examples, and then use them to train a better decoder. All right, so what I'm going to focus on in this talk is not the most sophisticated fancy ideas, but just focusing on the idea of, let's say we train a decoder by borrowing a classical architecture. What can we say? What theoretical guarantees can we give in that sense? So here's the setting. We have a block code, a linear block code described by a parity check matrix. So you can also represent it by the Tanner graph. Basically, number of variables nodes, number of check nodes represent the number of parity checks or the number of equations. And then I'm going to focus on belief propagation decoder for the rest of the talk. Okay. Why belief propagation? Well, again, I don't want to be contentious here and argue. This is one of the most commonly used algorithms for decoding. And the way it works is it computes the channel log likelihood ratio values and then does a sequence of operations for a certain number of steps and comes up with an estimate for the message bits. Okay. How do these work? There are specific equations you can write down if you know belief propagation. Again, I'm not going to spend time on this part of the talk. I'm hoping that you know already what belief propagation is. So essentially, it's trying to take estimates of what we believe is the right value of a given bit at any given iteration. And based on that belief, then we check. That's what the likelihood that given this belief about the bits, what's the probability that a given check constraint is satisfied or not? And based on that, we sort of go back and forth between updating the belief for the bit and checking whether the updated belief is going to satisfy the checks or not. And then we run it for, let's say, t iterations, right? So these are the classical variable node and message check node updates that they look like. And at the final end, this is what the decoded output looks like. Okay, any questions so far? All right, now this is what neural belief propagation looks like, which was proposed, I think, 5 years ago. So what it does is it makes the observation that doesn't this look very much like a feed-forward neural network? So what can we do to make it better? Maybe we can do generalized or weighted belief propagation, where instead of having fixed rules, we're going to do weighted updates. So wherever we see some incoming likelihood LLR coming in, we're going to multiply it with a weight. And same thing for this guy. And these weights are something that we can try to learn. So we show noisy examples, and then we borrow the architecture from belief propagation, but we sort of endow this network with weights, and the weights are learnable, right? So this is what we call as neural belief propagation, right? So of course, some parts of the things people keep as fixed, and again, there are reasons for doing some parts of the operations fixed, some parts of them trainable. Again, there is a lot of heuristic things involved here that I think over the years people have done, which layers, when they are made trainable, gives you the best bang for the buck. Okay. All right. So how do we evaluate performance of decoders? We look at block error rate or bit error rate. So BER for the remainder of the talk will stand for bit error rate for me. Okay. And neural belief propagation has shown to actually outperform belief propagation, especially in short to medium block lengths. Okay, so not like 10,000 block length codes, but let's say 500 to 1,000 block length codes, it actually performs much better than belief propagation. Okay. And since the original papers appeared, there have been a lot of subsequent work on this. So this neural BP based decoding has actually gained quite a lot of traction. So people have looked at offset, min-sum, quantized versions of neural belief propagation when the internal operations could be quantized. People have also looked at knowledge distillation and how to use a larger neural BP to a smaller neural BP to reduce complexity, and so on and so forth. So what is this talk about? This talk is about understanding, giving some theoretical bounds in terms of generalization gap of neural belief propagation decoders. So what do I mean by that? So let's say you take noisy code words generated at a certain SNR. Okay, let's say you pass them, you do a certain modulation format, pass them through a channel, and you generate your training data set, and you train your neural belief propagation decoder, and you get a very nice bit error rate of 10 raised to power minus 9. Okay, so this is what I'm going to call as BER training. Now, I want to understand that what's the expected bit error rate that I would really see. So this is just what I see on my training data set on a small set of noisy code words. So how does this difference look like? Okay, so of course, people have studied generalization gap within the context of statistical machine learning. Even Max in the morning gave a very nice talk. So by the way, I'm not an expert. So if Max is here, Please poke me. Okay. All right. So the question that we want to understand is, can we bound this difference? And we want to understand this difference. How does this difference behave as a function of the following objects? The training data set size, training iterations. These are standard things which people test, or they try to bound the generalization gap and try to understand behavior as a function of these things. More interestingly, we want to understand how the gap behaves as a function of the decoder architecture itself. If the parity check matrix is dense versus sparse, which one is easier to learn? Is a sparse parity check matrix easier to learn, or a dense one easier to learn? How does generalization gap behave as a function of the message length? How does it behave as a function of block length, as a function of code rate? How does it depend on the underlying SNR? So if you train a neural BP decoder at SNR of 5 dB, if I increase the SNR, does the training process become easier? So those are the questions we want to answer. Of course, you can imagine more sophisticated questions in this list, but that's for another talk and another set of papers, right? Okay. Yes, question.
Is the most important one, or
it's one of the most important ones? Yes. And I should say the others are, I mean, we are not going to tell you anything new here. The results, the dependence on the training data set side training iterations, I'm not going to tell you anything new. Only thing new stuff will be this. Okay. All right. So here is what my training data set looked like. I have some x1, x2 till xm. These are my noisy code words. And lambdas are my likelihood ratios. You can either view lambdas as the likelihood ratio, or you can also view them as the channel output. It doesn't matter. You can replace interchange either one of them. Doesn't matter. And then now I'm going to sort of bring in the terminology from statistical pack base bounds in machine learning. So now we are picking a neural belief propagation decoder. So we can view this decoder as a function which takes the channel likelihood ratio coming out from the channel output and mapping them to an estimate x. The goal is to find a good mapping f, which minimizes the expected bit error rate, right? So what is bit error rate? It's the Hamming distance between the f lambda and the actual x, right? Okay, so in the ideal world, our goal is to find the f star that minimizes the true risk, which is the expected value of the bit error rate, when lambda and x are drawn from a certain distribution. So distribution means, let's say you want to find a good decoder which works at SNR of 5 dB, then you would want the best f you can find for that channel condition, as an example, and that specific code, right? But in practice, of course, we don't do this. We do empirical risk minimization. So we, find an f which minimizes this guy. Okay. All right, so we can define two things. RBER is the expected BER of a fixed f. So think of a fixed f as a given neural decoder which has been trained, and R hat BER is the empirical BER of that fixed f over the training data set. Okay, and then my generalization gap is nothing but the difference of these two. Now I want to bound this difference for every f in that family of decoders that I can pick from. Okay, so these are called uniform convergence bounds. So I want this difference to be as small as possible for every f that I can pick from that family of decoders. The family of decoders is not governed by the decoder architecture that I borrowed from the classical world. Is it clear? Okay. So we are, of course, we're going to make some assumptions that the weights matrices that we were dealing with, we'll assume that the weights are bounded. The input to the decoder, that is the likelihood ratios, are also bounded. Second one is a little bit not so comforting, but we will deal with this in the second theorem. So first, let's deal with this one first, and then I'll come to the next one. Okay. All right, so here's the standard result. We haven't done anything here. This is a classical result which says that if I give you a function class f of t, so think of ft as all neural decoders which satisfy bounded weight property, then for every f in this family, this generalization gap can be bounded as some object here, RMFLT, which is the Rademacher complexity of this function class, plus some term which behave like 1 by square root f. Okay. Well, what is this RMFLT? This is essentially how correlated is the BR to random Rademacher variables, which is basically plus minus 1 with probability half, right? So this is Rademacher complexity. I know many of you know it here, but for those who do not, essentially it measures how correlated a function is to random uniform noise, which is plus minus 1. Again, I'm not being very precise here, but I hope it at least conveys something. So now the question is, well, we can just directly lift this result. We can do, there's nothing to be done. So now the question is, can we bound this guy? Can we bound the Rademacher complexity and understand its dependence on the same set of things? Training iterations, decoder architecture, and so on and so forth. Okay, so that will be my next step. All right. So what do we do? So first thing we do is the first upper bound this guy in terms of something called bitwise Rademacher complexity. That's our first tiny proposition. So what it says is that looking at this guy we can upper bound by the average of something. What is this? This is 1 by n. N is the block length. Remember, the output of the decoder is a n length object. Okay, one estimate for every bit. Okay. Now I'm going to define a very similar quantity, but now for the jth bit. So I'm going to look at the Rademacher complexity of the jth output of that vector. Okay, and then average this out. Okay, so the first claim is that we can show that the Rademacher complexity of the original function class is less than the average of the bitwise Rademacher complexity. Okay, this makes our life a little bit easy.
But this is fixing, so the so you get a vector of inputs, right, to this neural decoder. So are you giving me a Rademacher complexity by looking at that?
Okay, so let me clarify. This was defined as a correlation between the loss and the Rademacher adaptation. The loss was still a scalar, but the loss was dependent on essentially the whole vector. All right, lambda was the whole vector. But now I'm saying that I can upper bound this guy in terms of average of basically the same supremum and expectation sits outside, but now I have 1 by sigma I, and what sits here is the ith output of f and the average of it. Okay, so instead of taking the correlation between sigma I and the loss, I'm going to take the correlation between sigma I and the output of the decoder of the ith bit, which is still a scalar, and then average over the n things that come out from the decoder.
The loss doesn't matter. The loss is a big part of the Rademacher. Okay, I'm sure.
Yeah, I mean, I haven't put the proof here, but the proof is in the paper, so we can talk about that. Okay. So that's the first step. Again, this is not a big step, but nonetheless, it makes life a little bit easier. Okay, so what do we do next? So of course, the next step is to bound the bitwise Rademacher complexity. Okay, so we're going to do that next. Now, what we do, as Max taught us in the morning, we will bound this complexity first using Dudley and Propagation. Okay. So we define something called, again, it's not my definition. This is all out there in the literature on bounds of Rademacher complexity. So what is covering number? Covering number is the minimum number of, again, balls should be in quote here to cover a given space. In this case, we are not covering space, but we are covering a class of functions. So FT is a class of functions. So what is covering number informally? It's the size of the minimum set of functions you need so that basically at least one of them is going to be a good approximation of f at any input lambda. Okay, so this should hold for any lambda. All right, and then I'm asking that what's the minimum class of functions that can sort of approximate it within a given budget of epsilon. Okay, all right. And then there is a result which says that, you know, with this covering number defined, we can actually bound the Rademacher complexity, the bitwise Rademacher complexity in terms of complicated looking object, but nonetheless, it looks as a function of the log of the covering number. All right, let's leave people. Okay, so what next? Again, I have done, there's no innovation from our side at this point. What are we going to do next? We're going to now bound the covering number of the function class, which is derived from the decoder architecture, right? Okay, so let's bound the covering number. Now we use another property that if the function class can be written as a composition of functions, And it turns out for us, it is, because our function class is unrolling of the Tanner graph. And there is, one layer after another. And for our specific form, if the weight matrices, let's say U, V, and W, which are the learnable objects, if that satisfy a Lipschitz property, then the covering number for the function class F can be written as a product of the covering numbers of the individual matrices themselves. Again, this is a standard known result. What we show is that for neural BP decoders, we can show this Lipschitz property. Okay. So namely, there exists some rows, row W1, row W2, and so on. Basically, these rows correspond to some constants, which may depend on W's themselves. So that F minus F dash is less than a linear combination of the two norm of the W minus W primes. Okay, that's essentially the Lipschitz property. Now with this and the first fact, we can then bound the covering number for the bitwise function class ftj as the product of the covering numbers of these individual guys. Okay, so that's yes.
Can you remind us what are W3 and W4?
Oh, so this is just a generic statement of UVW. There are 4 types of weight matrices that are learned. There is a initial W in the beginning, a big W at the end, which combines the final thing for a decision. And then for every layer, there is a check node update, variable node update. So for every guy, there is W1, W2 for the first check variable update, then W1, W2 for the next one, and so on and so forth. Okay. So if there are T iterations in BP, there are 2 matrices per layer, and then 1 at the beginning, 1 at the end. So 2 times T plus 2 is the total number of trainable matrices. All right, so using Lipschitzness of the NPP decoder, we can then bound this as a product of these objects. And then, okay, so what next? What should we do next? Well, we should think about bounding these guys, right? That's what we're going to do. Now, this is where we're going to exploit the specific structure of the W's. Where are the W's coming from? W's are derived from the structure of the parity check matrix, the Tanner graph. Tanner graph is nice, it's sparse. We know the precise structure. It has DV non-zero entries in every column, and so on and so forth. And so that's where we will exploit the sparsity of the W to get an upper bound on the covering number for those individual products. Okay. So here's another result, again known from the literature, which we use, that let W be the space of all R by C matrices so that their L0 norm is Q and the bound of spectral norm being BW, then we can bound the covering number in terms of this quantity. Okay. I'm not going to prove this result. This is again a standard result. Now, with this in mind, then we plug this thing. Sorry, we take this result and then we plug it back in our previous expression, combine everything together, and then we arrive at our main result. So this is our main result, which says that the generalization gap for neural belief propagation decoder is bounded by this expression, which I'm going to tell you about in a second, plus other things which are standard stuff. So 4 by M, this is a standard pack bound or generalization bound that you get. Term in the generalization bound you get, again 1 by square root 2M. This is again a standard term. What's the new term? It's this term. So let's see what does this look like. It has, of course, a dependence on M. M is, remember, the training data set size. So we expect as M grows, the gap should reduce, which is good. Now it also shows something interesting, that N shows up, but N just doesn't show up exponentially. So this gap does not blow up with larger block lengths. It does blow up with larger block lengths, but mildly. All right, so it blows up at square root N. Okay, so square root N times another logarithmic term. Of course, it also blows up with T. T is the number of training decoding iterations. Decoding iterations for me is the number of layers in the decoder. Okay, so as the number of layers in the network grow, it also grows, but it grows roughly like order of T. Okay, it also grows with DV. If DV is the variable node degree, which means if DV is higher, my parity check matrix is more dense. So it's harder to learn more dense decoders for more dense matrices rather than sparse matrices. All right, any questions about the main result?
So where is DC?
Oh, so I mean, DV, DC are related to N and K. So, you know.
Where is K then? I was looking for the rents.
Where is K? K does not show up here. I think we may have loosely upper bounded it by 1 or something. Yeah. But yes, that's a good point. Actually, we have a corollary in the paper where we put all the 4 things together and sort of study the interplay between. But yeah, good point. All right. So, I mean, here are just some, cartoonish plots. We just took this expression, plotted it, and see what it looked like. Of course, as these are not real experiments. These are just taking the right-hand side of this expression and plotting them. So we see, of course, we go down as M increases, linear increase in the gap as the number of, as the width of the network increases, square root N increase as the code word length increases. For us, I felt this was the most interesting result. The reason why this was interesting is when we started working on this problem, we started using BC dimension and precursor to Rademacher complexity methods. All those methods gave us exponential dependence on N. So it was not clear to us when we started looking at this problem, can we get a better dependence on the block length? And so this is what we get, at least as of now, from this method. And also linear dependence on DV. Now, of course, I'm not claiming this is the best. There is, of course, room for improvement. And I'm not aware of any other paper which has done this analysis for neural decoders at this point. So I'm gonna, I don't know how much time do I have? 3 minutes. 3 minutes, okay, perfect. So the other approach, as I mentioned, one could use BC dimension. And again, I think there is pack-based methods one could use for this problem. Yes, question.
You mentioned about exponential versus linear. So what is even more interesting to me is the fact that N and M are growing at the same rate. Is there some reason for that the number of samples once it's more than the number of examples once it's more than the training, more than the block length, you start seeing like
not really. I mean, you still have 1 by square root M term here, right?
But that will be small, right? That once N and M are comparable and both are large, the first term will dominate. But let's say M is a large constant. Sure. And so something nice is happening around N equal to M, at least in this bound.
Right.
So, is there any?
I have no other deeper explanation beyond that at this point. Yeah, good observation. All right. So as I said, there are other possible approaches we can try. At least we tried 2 approaches, but we did not get at least satisfactory dependence on the block length using these methods. And this approach, pack-based method, is promising, but it's very hard to actually compute closed form expression and nice expressions which show sort of clear dependence on the decoder parity check matrix and its parameters. So this is a valid approach, but I don't know how to compute it or bound it, at least, as of now. I'm going to show you maybe 2 other generalizations. So we can generalize this easily for irregular parity check matrices. So instead of regular, if things are irregular, we can do that, no problem. As I promised in the beginning, if the channel likelihood ratios are unbounded, then we can play a small trick and also deal with this. The way to do this is, sort of do a conditioning on the event that likelihood ratio is unbounded, and then sort of sandwich that by a tail bound of cosine, and the remaining for the bounded case, you can then get the same bound and then optimize over the threshold that you pick for your LLR. Okay, so these type of tricks you can play. All right, I think that's pretty much what I have to say. And then since this is a trustworthy machine learning session, you may trust your artificial decoder. And this paper we posted on arXiv on Friday. And luckily, the next paper below our paper was Max's paper, a unified framework for information-theoretic generalization bounds. So we can learn from this and maybe apply it here. All right, on that note, I'll finish.
One or 2 quick questions.
Give some intuition on why this proof technique is better than fact-based or DC dimension, like why those doesn't work.
Anybody can help me here. So I think the Dudley integral is, I think, one of the main ingredients, right? I mean, it gives a logarithmic growth in in that covering number, as opposed to, I mean, there are several ways to count the same thing, but I think building to integral is much more tighter. That's my understanding.
Is that okay?
Yeah, sure.
You keep talking.
Okay.
So for these problems, how do you obtain the training data set? Because if you get training samples from like channel simulation, you can theoretically generate the samples and not worry about generalization.
Right. I mean, data scarcity, I mean, there's not much data scarcity in this setting. The problem is, how long do you want to train it? And how many noisy code words do you want to show? I mean, if the code has certain structure, people use these tricks like training on the all zero code word. So they don't show all possible code words in the space, but they show a small subset of code words in the space, and then, kind of noisy realizations in the all around it.
I'm hearing really the computation cost and data.
Good.
Okay, thank you, Ravi. Okay, it's my pleasure to introduce Ravi Shankar, who's giving the last talk today.